Okay, so the first topic that we're going to look at um, as the course starts is going to be a little bit of logic and set theory. Um, and I guess that's the main things for today. So we have some logic, a little bit of proofs and proof techniques. Okay, so those are the main topics. These are just like little introductions to each of these topics. You know, um, don't expect you to be expert, just expect you to get some feel for the math. We'll use these sort of things a lot more as we do actual proofs. I mean, not so much in this class, but as you move forward in the other classes. But this just gives you an intro and maybe a reminder of some stuff. So we'll start off with propositional logic. So propositions are sentences with truth values. I mean, that's basically what they are. So some perfectly good sentences don't have truth values, like watch out or is your name Jim, right? So those are not propositions. Phoenix is in Arizona, right, is a proposition. Phoenix is in Hawaii is a proposition, right? The first one is true and the second one is false. Okay, so still proposition though, right? A proposition can be false or it can be true. Um, some propositions can be always true, like it is either raining or it's not raining, right? Those are called tautologies, and sometimes you just call those trivially true because they don't really say anything, right? They're sort of just true by the nature of logic, so to speak. Um, so anyway, that's what a proposition is. Oh, some can be trickier. Like if I just say this sentence is false, right? That's a perfectly good sentence, right? And it seems to be saying something. But if it's false, then it has to be true, right? And if it's true, then it has to be false. So it can't really have a good truth value, right? So it's not a proposition, right? So there are some tricky ones. That's a well-known tricky one, which is basically called the liar's paradox. But the point is that's not a proposition. So that's not among the things that we'll be looking at. We look at what can be the values of propositional variables. And so that leads to the next thing, which is these propositional variables. And that's really just using variables to stand in for sentences. So we just use things like P, or Q, right? And so we might write things like P is, the cat has 4 legs, right? Or something like that. Right? So or we might write P equals, that sort of sentence or something like that, right? And sometimes you don't actually write anything. You just make up some propositional variables and use them for things. But they're variables in the sense that they can take values and the values should be propositions, right? So that's the idea. So these are just stand-ins for things that should be thought of as propositions. Okay. And so as so what do we do with these propositions? Well, we build them into more complicated compound propositions, right? And so there are logical connectives. So that would be like this little note. And there's a few of these. And for the most part, they're kind of obvious. But there's a couple that take a little bit of thought. So there's and. So this is and. There is or, and this is or, and there is not. And there's maybe various ways of writing not. Sometimes you write it with that little funny sideways L thing. Sometimes you write it with a squiggle. Sometimes you just write with a minus sign, right? So there's various ways. So in terms of notation, you have to sort of see what people are doing. Also with and, I mean, sometimes you write it with an ampersand. Let's see, there's other ways of writing and or there's another way of writing or is sometimes with just a bar. Like maybe you're doing coding, right? Those are really common for that. And sometimes for not even there's like this sort of like an exclamation point. So anyway, there might be lots of notation for these various things. Yeah, the main thing is how are they, like how are they used? So sort of intuitively, and so P and Q is true precisely when both P and Q are true, right? So there's not much tricky about and, okay? Or is a little tricky because in math, right, we say P or Q is true if either P is true or Q is true or both, right? So it's called the inclusive or. So that can be a little bit tricky, right? Because it's not necessarily the way you would use the sentence in English, right? So maybe you say, either the cat is sleeping or it's eating, right? Um, well, maybe that's a bad one. Let's say the cat is um, lying down or it's eating, right? But maybe the cat is both lying down and eating at the same time, right? You would still say that sentence is true when you're using this kind of mathematical or. Not is kind of the obvious thing. So something's not true uh, if and only if its negation is true, right? So that's kind of clear. The other really important one is implication, which we write with like an arrow, sometimes with a double arrow. And so this is like if something, then something, right? So this would be P arrow Q like that. This one's also a little bit tricky because this one is true. Oh, let's say it's false, right? Exactly when P is true and Q is false, and that's the only case in which it's false. Okay, so in particular, if P is false, right, this implication is always considered to be true. So again, that's different than you might use it in formal language, right? So like if the moon is green, then the earth is flat, right? So that's actually true because the moon is not green, right? A really important case is like if 0 equals 1, then whatever, then the Riemann hypothesis is true, right? It doesn't matter, right? Because that implication is true, right? Now it's definitely not the case that 0 equals 1, so that just doesn't happen. And in fact, a situation like that is called vacuously true. So if this hypothesis is just false, right, then this thing would be vacuously true. So, but it is a little different than what you might view as a informal use of the word implications, right? It's not like P causes Q or something like that. There's no causality. It's just this kind of formal thing. So these formal rules can kind of be expressed through these things we call truth tables. So let's look at that real quick. Let me just erase all this stuff. So in a truth table, you just have all the various possible truth values of a proposition. Okay, so if I want to make the truth table for P or Q, for example, right? So I would have P here, I would have Q, and then I would have P or Q, right? What are the possible values of truth for P? Well, there's true. I'm going to duplicate it twice because I have these two variables here, right? So I have false and false, and here I have true and false, and true and false. All right, so this is a little counting argument. There's two possible values for each of these things. So there's 2 to the 2 equals 4 possible pairs, right? So you have to consider all those pairs there, all right? And let's just make this little line here. So when is P or Q true? Well, so P or Q is true if both are true, right? So that gets a true. If either one is true, so that gets a true, and it gets a true, right? And then this one here is false, so that gets a false, right? So there's like the truth table for P or Q. And then you have similar ones for P and Q and not P and any other sort of composition you want to use, right? So there are some extra notes. Well, one big truth table is right here, so I'll talk about that. But let me just point out, where is the link? Yeah, okay, so there are some extra notes here that are slides that I used in another class and has lots more examples of this sort of thing. Let's look at one important one. Let's look at the implication thing, right? So let's have P implies Q. And I also want to look at, and I guess I should give myself more room to this because, so let's see, I'm gonna look at something with P and Q, and I want to look at P implies Q and P and not P or Q. Okay, so the main two I want to look at are those two. All right, so same kind of thing. I'll have true, true, false, false, right? True, false, true, false. So we're looking at all those. So when did I say, so this one's only false when P is true and Q is false, right? So this only here, right? This is false. So it's true everywhere else, right? When is not P or Q true? Well, that's going to be true exactly when. Actually I should have left myself a little bit more room. So let me see. Let me do this. Let me erase that line there and squeeze in a not P here and make these lines a little bit smaller. So it is not P here. So not P is false, false, true, true, right? So when is not P or Q true? Well, it's going to be true. It's going to be, sorry, when is it false, right? It's going to be false exactly when not P is false and, right, Q is false, because that was the only case, right? That's the only case that an or is false, is when both pieces are false, right? So that's going to be false exactly here, right? And this will be true and true. So everywhere else of these are going to be true. Whoops, and I just had a typo, righto. Notice that these two columns are exactly the same, right? So those are actually called equivalent propositions. So we could write here PQ is equivalent to not P or Q, right? So they have, and so what this means is it means they have the same truth tables, right? So this is like the truth table for this thing. This is a truth table for that thing. They have exactly the same truth table given, the various possibilities of true false for P and Q. Okay, and this is actually, I mean, maybe one sort of useful thing is there's a notation like this too, you'll see. So P if and only if Q. And this literally means, so sometimes maybe to make it clear that I'm making a definition, I'll just write, so this is defined to be, right? P implies Q, and Q implies P. So it means both of those arrows hold. And so it's actually the case that P if and only if Q is kind of equivalent to, and this is using the same notation for lots of things, but P is equivalent to Q. So it turns out that these are the same. So this happens, right? In other words, this happens if and only if the rows of the truth table are exactly the same. So maybe with just P and Q, it's not quite clear, but here I wrote this equivalence because they had the same row of the truth table, right? If I were to add in a line, let's see, I would have to, let me try to do this. So let me just cut all this stuff out. Okay, and let me try to like take this, let me move it down a little bit and let me make it smaller so I can squeeze in some more stuff. So let's say I tried to add in a line for P implies Q, and let's say implies not P or Q. All right, so I'm adding in that line there. Then when is this going to be, again, this has only one case where it's false. So that's really the case we want to look at. So when is this going to be false? So this will be false when this is true and that is false, right? That's the only place it could be false, right? But these actually have the same truth table, so that will never happen, right? So this would be true, 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 right? So those will all be true. And if I were to turn the arrow around and go the other direction, the same argument gives me true, 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 right, as well, right? So what I'm getting here is I'm getting that P implies Q if and only if not P or Q. Its truth table has just all truths, right? So this is just always true, right? So this if and only if here holds. Just means it's sort of equivalent to saying P implies Q is equivalent to not P or Q, right? So literally there is a difference. So this expression says that these two columns of the truth table are the same. This expression says that the row of the column of the truth table for this expression is all truths, right? So they literally mean something slightly different, but they essentially mean the same thing in practice, right? So very often we might write either one of those two things. So that's common. Okay, so I mean that's sort of the very, very basics of truth tables. Um, Notice that for let's say like how many, I mean we can do some sort of counting here. So if I'm just looking at, actually, let me just erase all this stuff. If I'm looking at like the number of different propositions up to equivalence, right? So let's call one propositional, let's say I have a proposition, a compound proposition in Q and P, right? So it's got two variables, right? And I've got, maybe it's equivalent to some other proposition in Q and P. Okay, so again, I mean, just to be explicit, this one might be P implies Q, for example, right? And this one might be not P or Q, right? So these are just some sort of expressions, right? With, you know, um, propositional variables and connectives, right? So some sort of compound propositions, and they're equivalent, meaning they have the same rows of the truth table. So up to equivalence, right? They're kind of the same, right? They're just correspond to the same truth table, more or less. So how many possibilities are there for things like that? Um, well, right, that's a question of how many different ways can I, map. So I'm saying we're looking at the truth table. So I've got a phi qp, right? And I'm trying to map it to a row of the truth table. So a row of the truth table has four choices of trues and falses, right? So it's like something, 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 right? There's four because there's two variables, right? In a truth table, there's going to be four. These Q will, Q can take true, true, false, false. P can take true, false, true, false. So all those combinations output, these four things here, right? So all together, right, there are 4 to the 2 or 16, right? Many kind of different compound propositions just up to their truth tables, right? So, some really basic counting here in terms of how many kinds of possibilities there are in these things. Um, you can kind of see here that in some sense, looking at this in this way, we're not really using this to do proofs. We're kind of looking at this as an algebraic structure in some sense, right? I mean, this is kind of doing math on the logic of that we use for doing proofs, right? So we're actually in the middle of doing proofs. We won't do so much of this stuff, but sometimes you do it. Let's see. In the notes, I have a little bit of comment on. Oh, well, okay. One important thing in the notes before I go to that. So let me just erase this again. So one important thing is this idea of, I mean, we want to kind of know important equivalences, right? So there are lots of important. So one important equivalence is this one, the one we've already shown, and I have indicated why this is true, right? So not P or Q, right? So that's an important equivalence. I'm sure it has a name. I actually don't know what the name is. Here's another very important one. Not P or P is true, right? So I could just say that, but I could just say is equivalent to true, right? That's just always true. So this is called excluded middle, right? So that one is sitting right here. De Morgan's rules are really important. By the way, this is controversial in some sense. There's a kind of mathematics called intuition, intuitionistic mathematics that throws this out, right? That says, well, we can only say not P or Q if we can kind of construct, something witnessing not P or Q. So when we get down to proof techniques later, we can look at an example where that actually comes up. But generally, this is considered just true. Okay. And then we have like De Morgan's laws tell you how to kind of push knots through ands and vice versa into ors, right? So not P and Q is actually equivalent to not P or not Q. Okay. And similarly, not P or Q is equivalent to not P and not Q. Okay. So lots of, those are the two De Morgan's laws. And then there's two distributive laws, right? So kind of different. You might think of or as kind of being like and you might you might think of or as kind of being like plus, and as kind of being like times. So you might think that multiplication distributes over plus, and you'd be correct, but actually it distributes in both ways, right? So we actually have p or Q and R. So here's one with three propositional variables, right? Is actually P or Q and P or R. And there are rules about when you can leave out parentheses, but I would say generally put them in if it helps understand what's going on, right? So I'm not I don't want to spend time talking about parentheses rules. And then we have a similar one here. So if I do P and Q or R, right, then I have P and Q or P and R. Right, so those two rules are the distributive rules, right? So how would we verify these things? We would write out the truth tables, in this case with three variables, so there'd be 8 rows, right? And you'd verify that the column corresponding to this had exactly the same truth table as the column corresponding to that, right? And then of course there's other ways of doing it too. Okay, but that's sort of the generic way of doing it. So propositional calculus is pretty straightforward in that sense, right? And it's used for building circuits and things like that, right? I mean, it's got some actual applications. One kind of useful application is this. If I'm given a proposition and I would like to know a particular form for that proposition, so disjunctive normal form is the form, and actually I have to get this right. So disjunctive normal form is the case where you have disjunctions of conjunctions of your variables, right? So you have a bunch of disjunctions of a bunch of conjunctions, right? So it's kind of writing it out. It's kind of like you thought of this as a sum of products, right? That's kind of the idea. And conjunctive normal form is the opposite. So you have conjunctions of disjunctions, right? And it's actually easy to write out these formulas. I mean, this is kind of a messy formula, but if I write out the truth table, so here's a big truth table of this expression over here, right? So it's that expression right there. So here's P, Q, and R, and here's all the various possibilities of P, Q, and R, truth values, right? So here I have to do, 8 possibilities of P. There's 4 variables, right? So there's 16 rows, right? So 8 values of P, of true, right? 8 of false. For Q, we're going 4, 4, 4. R is going 2, 2, 2, and S is going TF, 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 right? And that covers all the possibilities. And then here's R or S, and here's Q and R or S, and here's P or Q and R or S, right? So all those things there. And then we take all of these that have truths, right? So all of those, and we say we take the conjunction of these values. So here we would have P and Q and R and S. Here we'd have P and P and Q and R and not S. Here we'd have P and Q and not R and S, right? So you get the idea. So you go like that, and you take the disjunction of all those. So that's all of these, right? So these pieces correspond to rows of the truth table. So like here's P and not Q and not R and S, right? So this would be TFFT. So we come up here and we find TFFT somewhere. So there it is right there, right? And it has a true in the final column for that compound proposition, right? And that's the reason it's in this disjunction. Okay. Similarly, for the conjunctive normal form, right? You look at where all the falses are, right? And then what you do is, so here's like the first false. We have false, true, false, false. You negate that, right? So here, instead of putting, let's see, so that first one is here, right? Oh, you can't, yeah, maybe you can see I'm using a mouse and a pen. So I can't actually write on this document. So I've just moved that around, right? So there's the first row, right? So here it's, actually here's the first one, right? So it's false, true, false, false. And what we're going to put in is kind of the opposite of that. So we're going to be in P, not Q, R, sorry, P is P, Q, R, S, right? So P, not Q, R, S, right? So here, P, not Q, R, oh, that should be an, sorry, that should be an S. So there is a typo here. I need to go back and fix that. And so we put those in as disjunctions, and then we take the conjunctions of those, right? So it's kind of a pain to remember this, right? But it's actually simple. You write out the truth table, and then you just implement this thing, right? And so, I mean, this takes, this sort of puts these into kind of a normal form. That's what it's doing here. Okay. So it's useful for example, for building circuits. I mean, using these kind of things are useful for building circuits. Okay, so that's really kind of the basics for the general propositional calculus. Okay, so let's do a little bit of proofs, and then I'll make a separate video going into predicate stuff. So with proofs, we want to sort of look at this and how we actually use it. Again, this is still sort of formal compared to what you do when you're writing an actual proof. But basically, a valid argument is just a bunch of propositions, or they might be compound propositions, and then a final proposition. And the point is supposed to be that if I take the conjunction of all the hypothesis, right, and I look at this implication that gives me the conclusion there, right, then that should be a tautology. So in other words, in the truth table for this thing, that should be trues everywhere, trues up and down, right? So that's the idea. So that this implication being a tautology, always true, right, is what it means to say that this thing over here, the sequence of sentences, so to speak, is a valid argument. Okay, so again, that's kind of a formal, definition, but that is basically how we do math, right? And so to sort of express this some way, we tend to write it like this. So we have these hypotheses on this side, and they prove Q, right? So that's this little turnstile symbol is the symbol for proving something. Okay. And then so we have lots of rules of inference. This is no way a complete list of rules of inference, but maybe this list is complete enough. I mean, this is getting into more detail than we're going to do in this class. But modus ponens is a big one, right? So if I P implies Q and I also have P as my hypothesis, right, then I get to prove Q, right? In other words, I can say, well, P implies Q is true. P is true, right? So Q has to be true. So this is a valid proof technique, right? Modus tollens is kind of the opposite. If P implies Q and not Q, right, then I also know not P, right? Because it can't be the case that if P is true and P implies Q, then it can't be that not Q is true. Conjunction, if I have P and Q, then I get to say P and Q, right? If I have P, then I get to say P or Q for any Q, right? I get to introduce Q there in a way, right? So here's a little simple example. I want to show that I can prove not Q from P and Q implies R and not R and P, right? So remember these three things up there are the assumptions, right? So I get to just write down, this is assumed, right? It's one of my hypotheses there. Not R is assumed, right? It's one of my hypotheses right there, right? And then I get to use modus tollens, right? Because I have not R and I have P implies Q implies R, right? So I get to say that not P implies Q, not the hypothesis of this implication right there, right? And then I can use De Morgan's rules, right? So not P and Q. So here I'm sort of swapping out two things that we know are equivalent to each other, right? So that's how we use these equivalences, right? So I know that not P and Q is equivalent to not P or not Q, right? And then I know that not P or not Q is the same as P implies not Q, right? Again, that's because of this equivalence that we had. And then I have P, right, finally, so I get to conclude not Q, right? So this whole sequence of things is a valid argument, and the conclusion is not Q, right? So if I can take my hypothesis here and make a complete valid argument with all the steps there, and end up with not Q, then I still get to say these hypotheses proved not Q, right? So I mean, this is actually sort of what you do when you do a real mathematical proof. You just don't usually do it written down this way, right? Usually do it more just in English, right? And we'll see that as we actually do proofs. Maybe not so much in this class, but in future classes. But this is the backbone, right? This is sort of the theory there. Anyway, I'm going to stop this video and go make a separate one